In this segment, we're going to look at the rigid rotor. This will complete our array of model systems. So far, we have the particle in a box, which we will come to use for translational motion in a number of cases, as well as for describing electronic behavior in some very limited cases. We now have the harmonic oscillator, which is our model of choice for molecular vibrations. And the rigid rotor is going to be the system that we use to represent rotations of molecules. All right. As usual, let's start off by considering a sort of classical mechanics version of what it means to be a rigid rotor. Okay. Rigid rotor means that we want something that has only rotational motion, right? Rigid refers to the fact that if I was sort of conjuring this thing up, I could take a mass m, and out here I've got my mass m drawn on the end of the rod. The mass is attached to an axis by a massless rod of some fixed length r. The fact that r is fixed is what makes it a rigid rotor that says the distance of the rotating mass from the axis is not changing. My mass then just rotates in a plane around that point. Right? And so as shown in the picture, we have our rotational motion. It's got whatever the speed that it's rotating with, and there's an angular momentum associated with that. That is, in this case, in the vertical direction as my particle rotates counterclockwise in the picture. Okay. The moment of inertia for this system is just mr squared, and the kinetic energy is I omega squared over 2. Okay, where I is the moment of inertia, omega is again an angular frequency, and that gives us that result. And then the angular momentum associated with this would be I omega, right? In the case of the classical system, it seems like all energies would be allowed, right? If we actually had this system, if we were going to give this a push to get it started, and if we had it somehow configured so that it was a resistanceless, frictionless system, then we could just give it an infinitesimally greater or smaller shove, and it would change its rotational speed by some infinitesimal amount, right? So there's no limits, as usual for classical systems. There's no quantization. There's nothing that would seem to restrict the energies that my system could take on. If I want to build the quantum mechanical rigid rotor, we're going to need a Hamiltonian for it, like always, okay? In this case, my rigid rotor should have only kinetic energy, right? Because it's potential energy. There's no interaction between the mass and the axis of rotation or anything like that. It's just a fixed distance. And so my operator is just the kinetic energy piece. In this case, it's written so that it would be in circular coordinates or polar coordinates, mainly because that's the system that would make sense for this problem, right? So phi is an angular coordinate for where the mass is as it makes its way around the circle, right? A solution to that would be this equation written down here. So the general form is just e to the I m times phi. The m sub l is going to be a quantum number that arises here. I'm going to go ahead and call it m sub l. I believe that's what your textbook does, and that is a symbol that is often used for describing this, and so we'll go with that one. The n out here is just the normalization constant. Okay, so that is a solution to this. And then we have to try to develop what would be the restrictions, if any, on what my m sub l can be, right? I'm going to do the normalization constant first, I guess it looks like. The range of phi values, phi is this angular coordinate, right? So it can go from 0 to 2 pi. If it goes to 2 pi, then it's gone all the way around the circle and it's back where it started, right? I take my normalization integral and I need to do the complex conjugate because I do have an I term in there, right? So I get a minus I and a plus I in the exponents. I do that and I get that my integral with the n in front of it, I get 2 pi n squared for the integral, and I need to force that to be equal to 1 to get it to be normalized, right? And to do that, my normalization constant needs this value here. Right? So if I stick that in front of the e to the I m phi equation, I get this, which should be my form for the wave function. Right? It's now a normalized wave function. We still have not confronted what, if any, might be the limitations or the restrictions on the values of m sub l. All right? And so it's time to take that up, I guess. So if I want to find the energies that correspond to those, I can again just find the eigenvalue, right? And so we take the Hamiltonian, do H psi. When we do that, I've just sort of gone with written out equations here this time, I think it looks like. So I've got over here is my collection of constants. This piece in parentheses, that is, that's my second derivative, right? And so that says if I take that second derivative of this, I'm going to get, the I is going to come down twice along with m sub L twice. So I'm going to get minus m sub L squared in front of the exponent, right? Take that thing and then it's rearranged a little bit. This piece here is the original wave function, right? And that means that this is what I get for my eigenvalue. So that's the energy, right? The restriction on the wave function, what has to happen is we have to remember that wave functions have to be continuous, right? For the wave function to be continuous, it has to be true that the wave function at phi and at phi plus 2 pi have to match, right? That means that as I go around the circumference, my wave function has to repeat itself, right? It has to come back in phase with itself. If it doesn't, first of all, it would violate the rule that says wave functions have to be continuous. Second, if we just said what would happen if it did that, what would happen is the wave function would begin to interfere with itself, right? And over time, it would kill off all the amplitude, and I would get that the wave function had vanished by not repeating, right? And so in order to get that restriction to be satisfied, it turns out the allowed values of m sub L take on this set of things, right? So there's a 0, and then there's plus or minus 1, plus or minus 2, and so on. Okay, so a different set of allowed values than the other quantum numbers we've seen, but the same sort of arguments give rise to them. Okay, this particular version of the harmonic oscillator is not the harmonic oscillator, of the rigid rotor, is not the most applicable or useful, and the reason for that is that it restricts the rotational motion to be in a plane, right? If we actually have a molecule and it's just in space, right, it's not restricted to only rotate to stay in some plane, right? We expect it to be tumbling every which way if we could watch a molecule over time. And so this model is not really what would be happening. It's a sort of a two-dimensional rigid rotor, right? So to generalize to 3 dimensions, we're just going to do a little bit of declaration of what would happen, okay? If we look at the 3-dimensional case, the first thing that happens is for rotation in 2 dimensions, I got one quantum number, right? Effectively because the only variable was the position, right? Since it was a rigid rotor, the distance part was fixed. So there's really only one variable, so one quantum number. Go to 3-dimensional rotation. Now I've got 2 degrees of freedom because I've got 2 different directions I could set for this, right? I get 2 quantum numbers. The usual symbols for those are J and M sub J, right? And I'm going to use those symbols here because, frankly, we have too many things that we've called N already, and it's going to be best to just go ahead and use the real things. The allowed values of J are 0, 1, 2, and so on. So whole numbers starting from 0. The allowed values from M sub J, this has something that we haven't encountered before in our tour of quantum numbers. The values that are allowed for M sub J depend on J. Right? So M sub J goes from minus J up through plus J with 0 in the middle. Right? Notice that this says there will always be 2J plus 1 values. That's because I have J negative values, I have J positive values, and I have a 0 in the center. Right? So for J equals 0, I get just one possibility. M sub J must be 0. For J equals 1, I have minus 1, 0, or plus 1, right? So I have 3 choices, and so on. Something that is analogous to this is what happens, for the M sub L quantum number for atoms, which is the one that says how many orbitals are in a subshell for each type of orbital, right? So for an s orbital has L equal to 0, and so its M sub L has to also be equal to 0, right? So there's just one s orbital in each n shell. If I have p orbitals, they come in sets of 3, because just like for J equals 1, I get 3 possible values of M sub J, I get the same thing for M sub L. So that's a situation you're a little bit familiar with that works the same way. The energy expression turns out to depend only on J. So M sub J says I get multiple states for all of the J values other than 0, but their energy is always set just by J. This again is somewhat analogous to the fact that when I get a set of 3 orbitals, say in the 2p subshell, they all have the same energy, right? Same thing happens here. So my energy expression looks like this. It's got J times J plus 1 in front of it. Note it's got the reduced mass again, the same mu as we used before. R is the distance between the 2 masses. That's going to be a bond length, right? And it's got h bar up there. The 0 point energy in this case is 0, right? Because if I put in the smallest value of J, that's 0. When J is 0, then this piece, the J term, is 0, and that makes the energy 0. So I can have a 0 energy state. We often use a piece for this. In talking about these, we talk about what is known as a rotational constant. Pretend I left enough room to write rotational there. Right, this B is a rotational constant. It's handy because it corresponds to this term here, right? And so it's going to tell us something about the spacing between these energy levels, right? The increments in which they are apart, and that makes it a handy thing to talk about for doing spectroscopy. So we'll often mention that B rotational parameter, and that's all it is h bar squared over 2 times the moment of inertia. Okay. This is a system that has degenerate states, right? We met up with the idea of degenerate states earlier when we took a quick look at the particle in a 2 or 3 dimensional box, right? Where we had more than one quantum number and we got some states that just by coincidence had the same energy, right? So in the 2-dimensional box, when we had states that had the 2 quantum numbers, had one of them be 1 and one of them be 2, say. I could have 1, 2, or I could have 2, 1, and both of those would have the same energy. Again, the word for that is that they are degenerate states, okay? The energies for the rigid rotor are going to be degenerate for everything other than J equals 0, right? Because I have multiple M sub J values. And so let's think about what the energy level diagram would look like. I didn't actually put it in here, but we can sketch one. Energy increases going up, right? At the bottom, at E equals 0, I have J equals 0. And for that energy level, I have just one state, because when J is 0, M sub J has got to be equal to 0 as well. If I go up to J equals 1, I now get 3 possibilities, which I'm just going to draw them side by side like I might draw p orbitals and say that's J equals 1, where each one of those side by side lines would correspond to an M sub J value. Right? If I went to do J equals 2, I would have to draw 5 lines because I would have 5 different M sub J values, right? Because I would have -2, -1, 0, 1, and 2 for J equals 2. Right? Those different energy levels are all degenerate. They can only be told apart if you take the atom, or in this case, the rotating molecule, and you put it in an electric field or a magnetic field. That would impose a directionality on it that specifies an axis, essentially, and that would make those different rotations orient themselves with respect to the field vector for that electric or magnetic field. So, because it's rotating in 3 dimensions, another way of talking about the M sub J quantum number is that it's the orientation of the rotational axis, or alternatively, it specifies the projection of the angular momentum value onto an axis. Right? So when I say if I put the molecule in a field, if my molecule is rotating and if I put an electric field, say, that's oriented like this, then the diagram represents how my different M sub J's are going to arrange themselves, right? The M sub J equals 0 case is going to precess in a plane in there where its angular momentum vector is along the field axis. The other 2 values, if I had the case that J equals 1, are going to orient themselves with and against that field so that the projection of their angular momentum vector is equal and opposite along this axis, right? And that would be the angular momentum vectors associated with those rotations, okay? the degeneracy is there normally, and again, if I put the molecule in an electric field, then I get this separation that exists there. This is a model for molecular rotations, right? Again, the simplest thing to think about is a diatomic molecule, because then I just have my two masses. I'm using the reduced mass for the mass because I want to think about it relative to the center of mass, right? Just like vibrations, when I talk about rotational motion, the center of mass of the molecule is not supposed to move, right? So if my pencil here is the molecule, as it rotates, if it's a homonuclear diatomic, then the center of mass, of course, is right at the middle, and it would just rotate about that point, right? If one atom is heavier than the other, then the center of mass will move towards the heavier one. It would still rotate about that center of mass point, okay? Rotational energies are relatively small. They're smaller than vibrational energies. You sort of know from experience that vibrational spectra show up in the infrared. Right? If you want to see a vibrational spectrum, you use infrared radiation. If you want to see a pure rotational spectrum, you actually need to do this in the microwave region of the spectrum. Okay. Gosh, as a little bit of an aside, microwave ovens actually operate because the wavelength of the microwaves in the oven cavity is set so that it's in resonance with an absorption in water. So water molecules will absorb those particular microwaves very strongly. What that excitation does is it makes the water molecules rotate. It deposits energy into them that way, and that energy then gets dissipated into the food, and that's what heats it up. Right. That's also why some foods heat up much more efficiently than others. Basically, it depends on the moisture content, and something that has more moisture will be taking in more energy in the same window of time, as opposed to something that has less moisture, because without water, it doesn't really get to absorb that radiation nearly as much. So what are we going to do? We're going to find the wavelength of microwaves needed to induce a rotational transition from J equals 0 to J equals 1 for carbon monoxide with the normal 12 and 16 isotopes. We use that same molecule in an example in the harmonic oscillator video. And so I've just grabbed from there where we calculated the fact that we're going to use that number for the reduced mass. Okay. I've also specified here a bond length, which is 1.13 angstroms, or 1.13 times 10 to the minus 10 meters. We're going to need that to do the calculation. Okay. So that's what we're going to calculate, is what is the wavelength of microwaves that would correspond to this transition. Like any spectroscopic transition, when we look at this, we're looking at an energy. We want an energy that corresponds to delta E. Right? What do I know? I know that Ej, what I'll call what is the energy for state J, is equal to J times J plus 1 times H bar squared, let's just say over 2 mu R squared, right? And that's the energy overall. I want to say then, I'm interested in going from J equals 0 to J equals 1. Right? So if I take this and just put in the values, E0 is going to be equal to 0. Because there is no 0 point energy, and because if I put 0 in there for the J term in front of J times J plus 1, it's going to quickly take me to 0, right? If I do E1, that's going to be equal to 1 times 1 plus 1 times my collection of quantities there, H bar squared over 2 mu R squared, right? What I want is, and if I take this thing, I can multiply that out or simplify that and just say that I get 2 up here and 2 there, right? So this is just equal to H bar squared over mu R squared. And so delta E, for going from 0 to 1, is just the difference in those things. So I'll say E1 minus E0. And in this case, that's just equal to E1. So it's equal to the H bar squared over mu R squared. All right, so that's the energy. What I want is actually, I want a wavelength that goes with that energy, right? I can relate those, I can remember that E is equal to hc over lambda, and so lambda is equal to hc, it's really an H, I swear I made an H there, hc over, in this case, delta E, I'll say. So I'll add a delta over there too to be somewhat consistent, right? And so I could take those things and put things into place for this because I have I have actually, I could say that my lambda therefore is equal to hc over delta E, which is hc over this collection of things here, h bar squared, and I'll put mu r squared on the top, I guess, to do that. This is a little bit awkward looking because it's got h on top and h bar on the bottom. So let me actually say that I could rewrite that to say this is hc mu r squared up here. If I take the h bar squared down there, I could make that into h squared over 4 pi squared. And then I could cancel one of those h's and get myself something like 4 pi c mu r squared. All of that is just over h. All right, that gets me ready to put in numbers. I guess I've kind of put off the numbers for as long as possible. So this is equal to, oh, my 4 pi should be squared, sorry. This is equal to 4 pi squared. I've got c, which I'm going to write in 3 times 10 to the 8th. I've got mu r squared up there. I know that mu is equal to 1.14 times 10 to the minus 26th. Sorry, my writing is failing me again here. I was thinking I was getting better at that, but perhaps that was just wishful thinking. Okay, and then I need r squared, where r is the distance, so that's 1.13 times 10 to the minus 10th. That's in meters, and that's squared. All of that is over Planck's constant, which is 6.626 times 10 to the minus 34th power. That's in joules seconds. That really does say seconds, believe me. If I multiply all that out, my notes tell me that I should get 2.6 times 10 to the minus 3 in meters. Which I could also write as 0.26, let's say, really doesn't like it when I try to write near the edges. That's in centimeters now. So that's a fairly unusual looking wavelength, right? Remember, we're in the microwave part of the spectrum. These are photons with very low energy, so they're going to have much longer wavelengths than, say, visible light would, right? So things that are on the order of centimeters are actually going to be about what I should expect for a microwave wavelength. Okay, to do that calculation, I have to remember a couple things. I have to remember that in the spectrum, the energy that is absorbed, or the wavelength that is absorbed, corresponds to the difference in energy between two states, right? In this case, that difference of energy happens to be equal to what was E1, the energy of the top state. That's because for these rotational states, there is no 0-point energy, no energy corresponding to the lowest energy level. And so my delta E is the same as the energy in the upper state, okay? Let's see, we have, in closing for this segment, what I have is just a comparison of the energy levels for the three model systems we've taken up, right? I've got the particle in a box, the harmonic oscillator, and the rigid rotor. Okay, I have not included the degeneracies for the rigid rotor, and I'll talk about those in a second on top of this. But for the particle in a box, I get energy levels where the first one is at some finite energy above zero, right? So I have a non-zero ground state energy there, and my energy levels get farther apart as I climb up the energy ladder, right? For the harmonic oscillator, I again have a non-zero ground state energy, right? My energy levels in this case are equally spaced. The rungs on that ladder don't drift further apart or get closer together. They stay uniformly spaced, just like an actual ladder would. For the rigid rotor, I have my ground state energy is in fact right at zero, right? So I get a zero there, and then I get energy levels which get, again, progressively farther apart as I go up. Why is that? That's because my energy expression for this one has that J times J plus 1 piece, right? And as J increases, then J times J plus 1 grows faster than J does, right? And so the spacing goes up as the thing runs. If I were to look at the degeneracy, for the ground state, it's 1, meaning there's only one state there, right? It's not degenerate. It's just a single state. For J equals 1, I'm going to get 3, right? For J equals 2, I would get 5. For J equals 3, I would get 2J plus 1 would be 7, and so on, right? And so this would keep going up in this way as I go. What am I up to? 1, 2, 3, right? Yeah. And so I would get progressively more each time I go up there. Those numbers, the 1, 3, 5, and 7, again, those match up with the fact that as we go from S to P to D to F subshells, we have the same thing. That's not rotational motion, but it is related to the angular momentum of an electron in those orbitals. And so there are similar arguments at work for that. And since you're more familiar with those ideas because you've been seeing them longer, I think it's perhaps useful to make that connection to these. Okay. All right, where we are now, we have an array of model systems. We have the three that are, whose energy levels are depicted there, which we will be using to describe various types of motion, types of energy in molecules. Right? In the next module, what we're going to do is we're going to take up a closer look at some spectroscopy, particularly IR spectra for so-called row vibrational spectra, where we're going to be looking at changes in the rotational and vibrational quantum numbers happening at the same time. That's a somewhat complicated topic, and so be ready to spend some time thinking about what's going on in that next module. Thanks.